Okay, so where we left off, we said energy can be taken in during a chemical reaction that would be an endothermic reaction. In short, essentially, during the chemical reaction, the substance gets cold. It actually requires heat for the chemical reaction to occur. So that would be an endothermic reaction. There's other reactions that are exothermic reactions. In an exothermic reaction, heat is giving off. It's like an explosion. You could say like fireworks or something like that. Heat is given off in most and many chemical reactions, which would make it exothermic. Some chemical reactions take in heat, which makes them endothermic. For example, some of the cold packs that you have to twist, they get colder. That makes it an endothermic reaction. Sparklers, fireworks, explosives, things like that, those are all exothermic reactions. So they give off heat as they go through the chemical reaction. Sorry, that's the bell here at our school. And remember how we talked about the law of conservation of mass? Um, this is similar, but not exactly the same. This is about activation energy. In other words, some chemical reactions, just because the chemicals are there together, doesn't mean that the chemicals will start reacting on their own. They actually require some energy. Think of a sparkler for a second. You can have a sparkler and it's on the end of the little metal wire and you're like, yay, but nothing's happening. It requires activation energy in order for it to get started. This is kind of a diagram of activation energy. Um, this person is pushing this rock just a little bit up the hill, and then they're getting a lot more energy out of it. It's because the chemical reaction is giving off all sorts of energy, kind of like a sparkler, like I said. It's got all this chemical energy in there, but it requires you to get things started. Once you get things started, called the activation energy, it's the amount of energy required to begin breaking the bonds to start a chemical reaction. So once you get that chemical reaction started, the chemical reaction keeps going until it's finished. Notice in this video, potassium chlorate is heated in order to begin the chemical reaction, then a great amount of energy is released. So in this video, there's actually a gummy bear. And the gummy bear is put in the potassium chlorate. And the thing is, the potassium chlorate, if you just stick the gummy bear in the potassium chlorate, not a whole lot happens. You actually have to heat up the potassium chlorate a lot. So you have to add some energy. And then after you add some energy, you get a lot of energy in return. And most of that energy is the chemical energy that's stored up in the gummy bear. So it's the gummy bear chemical reaction. We're going to pause for just a moment and you can watch this video. Okay, pause is over. Hopefully you enjoyed that video. And let's go on to some more information about chemical reactions. This is all about the rate of a chemical reaction, or the speed at which a chemical reaction takes place. For example, some chemical reactions like rust, it might take years and years and years for that chemical reaction to take place. Other chemical reactions like explosives, they occur like that. So there's different factors that determine the rate or the speed at which a chemical reaction takes place. So let's talk about the factors that affect the rate of chemical reaction. One of those factors is the temperature. For example, baking cookies or bread, the decomposition of roadkill, I know that sounds gross, or rusting of metal. Think about it here for a second. Roadkill, does it decompose faster on a hot sunny day? Or does it decompose faster when it's extremely cold out? It decomposes faster when it's hot. So usually an increase of temperature accelerates the rate at which a chemical reaction takes place. Maybe you've heard that you should keep batteries in your refrigerator. That's true, because refrigerators, because they're colder, they have less heat, they actually slow down the rate of a chemical reaction. That's why I put my milk in the refrigerator. If I keep milk out on the counter, it warms up. The chemical reaction inside the milk accelerates and the milk spoils quickly. You put it inside the refrigerator, it slows down chemical reactions. It takes longer for the milk to spoil. So the colder it is, usually the slower the chemical reaction. Another thing that changes the rate at which a chemical reaction occurs is the concentration. The greater the concentration, the faster the chemical change. Concentrated acids react faster than weak acids. So when I say concentration, if you have a really, really dilute acid and you pour it on a metal, not a whole lot's going to happen. Maybe over a long period of time, you'll get a little bit of a reaction. But if you have a very highly concentrated acid, I mean, very, very strong acid, and then you pour it on metal, you're immediately going to see bubbles. You're immediately going to see some gases given off. It depends on the concentration. So the higher the concentration, the faster the chemical reaction. Same thing with like if you had baking soda and vinegar. You put in a tiny bit of baking soda, the chemical reaction is not going to happen very quickly. It's going to slow down. But you put in a lot, um, and you have a higher concentration, it's going to occur faster. Also, the surface area. The greater the exposure of the reactants to each other, the faster the reaction will occur. Think of it this way. If you had trying to think of the best way to explain this. If you had like gunpowder in a block, or if you had, let's say metal in a complete block, and you said, hey, I'm timing to see how long it's going to take for this metal block to turn into rust. You're going to be there for years and years and years and years. But what if you were to take that metal block, put it in a blender, and blend it up into little itsy bitsy shavings, and then you said, I'm going to see how long it takes for these little itsy bitsy shavings to rust. The itsy bitsy shavings are going to rust much faster. Why? Because there's a lot more surface area. There's more metal touching more air. And since there's more metal touching more air, the chemical reaction is going to happen faster. And then lastly, a catalyst. A catalyst is something that actually makes a chemical reaction start or makes it happen faster without undergoing any permanent chemical change itself. The best way I have explaining this is with people. Let's just suppose there's Billy and Gus. And Billy and Gus, they're friends. But Sarah comes along and says, you know what, I think Billy's really kind of cute. Now, Billy and Gus were getting along just fine until Sarah got there. Once Sarah got there, Billy and Gus, they're hitting each other. They hate each other. They're very angry at each other. They're fighting over this girl. So what actually started the argument? It was Sarah, the girl. But was Sarah in the argument? Was she an arguer in the argument? No. Sarah was just the catalyst for the argument. She made it happen. There's catalysts for chemical reactions, and the catalyst for a chemical reaction is something that makes the chemical reaction happen. And there's a video. I'm going to put a link to this video, but real quick, before you click this link to this video, I do want to apologize. At the end of this video, there is a foul word that is bleeped out. This video, it's a great video, but unfortunately, there is one word in there that should not be in there, and please don't be offended by that, or if you want, you can stop the video when there's like 15 seconds left, and you won't hear that offensive stuff. But it's a word that's bleeped out, and it's just, I don't know why it's there. Okay, we're almost done. A physical change. A physical change is a change that any change not involving a change in the substance or the chemical identity of a substance. For example, changing the size, the density, the color, the melting point, the boiling point of an object, those are all physical changes. I should give you some examples here, and I will in a second. The physical properties of a substance may change, but not its chemical properties. For example, melting ice. Ice is H2O. It's frozen water. But when you melt it, it's still H2O. You didn't change it chemically. You changed what it looks like, yes. You changed its density, yes. You changed its melting point, yes. But you did not change what it is made of. And if you're not changing what it's made of, that's a physical change. Same thing if you're cutting this log. You cut this log and you turn it into wood shavings. You didn't change what it's made of. All you did was change the shape. So it's still wood. It's just in little tiny shavings. Now, if you burn it, well, that's different. If you burn it, that's a chemical change. But in this case, simply chopping it or cutting it, that's a physical change. Sharpening a pencil, it's still wood. It's just in the form of shavings. Or breaking glass, it's still glass. It's just in the form of glass pieces. You're not changing the substance that it's made of. You're just changing the shape. You're changing some properties about it, but you're not changing what it's made of. So a physical change does not change what something is made of. And I think that brings us to the end of our very last slide. And don't forget to watch those videos that I've included in here. They're a very good learning resource. I will see you in class.